Welcome everyone to lecture 32 of sound waves. Now we have already talked about how waves travel, and we have also discussed that there are two kinds of waves depending on how they propagate in a particular medium. Propagate meaning how a wave source uh, transmits its energy from point A to B. It can be in the form of transverse wave where the propagation is perpendicular, this is the speed of propagation, is perpendicular to the oscillations, okay? And it can also be longitudinal, where the propagation direction is parallel to the oscillation direction, all right? So sound is an example of longitudinal waves. It travels in a medium by producing longitudinal waves, as shown here. Longitudinal waves basically produces oscillations of molecules of a particular medium through which the wave is traveling. And let's say these are air columns and they propagate in air. These air molecules are energized, which cause them to vibrate by a sound source producing the sound. Their direction of oscillation or vibration turns out is parallel to their propagation velocity. So they're vibrating such like that, and they're propagating in the rightward direction. So they're parallel, all right? This vibration and propagation produces regions of high pressure of molecules clustered together. We call these regions compressions, and regions of low pressure. We call these regions rarefactions. The middle the middle of the compression to the middle of another compression is one wavelength, or the middle of a rarefaction to the middle of another the next rarefaction is another wavelength. All right. Corresponding to transverse waves, we can picture the crests or high points of the wave to be the thick of the compression. So these crests are the thickest parts of the compression regions, and the thickest parts of the rarefaction regions becomes our lowest point of the wave. Okay, the troughs of the transverse waves. This is just a picture that helps us to look at longitudinal waves with a more familiar sort of transverse wave picture. The speed of sound waves, the speed at which sound waves propagate in a medium, depends on two things: the medium properties. For example, air is a different medium than water, so the sound wave will have different speeds in air and water. And also, the speed depends on temperature. For example, at 0 degrees Celsius, the speed is 331 meters per second, while at 20 degrees Celsius, the speed of sound is 343 meters per second. 20 degrees Celsius is usually taken to be the room temperature, and if you're not stated any temperature but you're working with sound waves, usually we choose to work with this speed. 343 meters per second is considered to be the speed of sound because that is the speed at room temperature. Generally, though, there is a formula or equation that helps us find the temperature at helps us find the speed of sound at different temperatures. The formula is given to us as V is approximately equal to 331 plus zero point 0.6 times capital T. This T is not the period, this is temperature. And temperature is measured in SI units in degrees Celsius, okay? And this is the sound speed. It's 331 plus 0.6 times T meters per second. Okay, now it's time to go check out an example of how this works. So we have here the example, which tells us that there is a camera which focuses using ultrasound, a type of sound wave, with the precision focus occurring at 20 degrees Celsius. At this temperature, the camera focuses very precisely. What happens at 0 degrees Celsius? That is, how far off focus is it at 0 degrees Celsius? Now, at 0 degrees Celsius, we just learned that the speed of sound is 331 meters per second. All right. So what is the speed at 20 degrees Celsius. We also learned that, but let's just use our formula to see that our formula works. V at 20 degrees is equal to 331 plus zero point 0.6 times the temperature in Celsius, which is 20, given to us here. This turns out to be 343 meters per second. So our equation works for any temperature. Okay, even 20 degrees Celsius, it comes out as it should, 343 meters per second. Why are we finding speed? We're finding speed because we know that position is related to speed. By the equation, position is equal to distance or speed times time. Okay, this is what we know from kinematics, correct? So if we can find out the change in speed, we can just say how far off the focus or positioning of the camera is. All right. So let's check out what the difference in speed is. The speed is different by, and we can calculate in percentages. So change in V over V times 100. Now this is the original, or this is actually the V20. All right. Now the change in V is V at 20 degrees minus V at 0 degrees over V at 20 degrees times 100%. All right. This comes out to be 343 minus 331 over 343 times 100%. Why are we putting this V at 20 degrees Celsius in the denominator? Because that is what we want to know. That is the temperature at which we want to know how far the speed has changed and how far the positioning of the camera focus has changed. This comes out to be 3.5%. So this tells us that there's a difference in speed, that the speed of sound of ultrasound is 3.5% off at 20 degrees Celsius. Hence, the positioning will also be off by around 3.5%. Okay. Let us now study some sound properties. Sound properties include pitch of the sound. Pitch is basically a quality of the sound, or you can think of it as how shrill a sound is. All right. For example, if the frequency of a sound is higher, then the pitch is higher, and that results in more shrillness of the sound. And if the frequency is lower, then the pitch is lower as well, and this is less shrill. All right. Okay. So this can be also be thought of as a very thin voice when speaking or singing. This can be a very thick voice when singing or speaking. Okay. Now the pitch is related to frequency, and there are specific frequencies that are given specific names. Example, 20 hertz to 20 kilohertz. This range of frequencies is termed the audible range. This is what humans can hear. Humans cannot hear any frequency beyond this range. All right. And above the upper limit, above 20 kilohertz, all the frequencies are called ultrasonic. This is used by bats to track themselves. And anything below 20 hertz, the lower limit, is called infrasonic. All right. These are not accessible to the human hearing system. The second sound property is loudness. Loudness is related to amplitude. It has no relation to frequency. Higher the amplitude, greater the loudness. Then comes intensity and intensity level of the sound. We have already talked about intensity of any kind of wave. Now, specifically, we will try and talk about intensity of a sound wave. Now, the intensity level is basically how the intensity of the sound is perceived. And it turns out that the sound intensity is proportional, not proportional, not proportional to the loudness. For example, if loudness goes from L to 2L, that is, you're doubling the loudness, intensity is not doubled. All right. So it is not a direct relation. It is not really doubled. Rather, it is increased by 10. It is 10 times more. So doubling the loudness causes a 10-time increase in intensity. This factor of 10 makes us realize that intensity would be much easier to think of in the case of sounds if we thought about logarithmic scales, which are scales of increments of 10. So usually we have scales of 1, 2, 3, and so on and so forth, or 5, 10, 15, and so on. Logarithmic scales are basically increments of 10, 10, 20, 30, and so on and so forth. Okay. So due to this, we define our intensity level for sound waves. This is measuring the intensity, how the intensity is being perceived for specifically sound, and we call it intensity level. It is measured in decibels, denoted by small d, capital B, and the formula for intensity level is beta equals 10 decibels times log of I over I naught. What is I naught? I naught is lower limit of the human hearing. So the human hearing cannot hear sounds any below this intensity, 10 to the minus 12 watt per meter square. The unit of intensity, 10 watt per meter square, is still the same. Intensity, our definition for intensity is still the same. Intensity is defined for all waves as I equals power over area. So intensity is defined as power over area. However, the intensity level is defined using beta or decibel level. Okay, so these are sort of different things, and based on how the sound intensity is being perceived by the human hearing. Let's talk less about this and look at the example to make this thing clear. All right, here we have an opera singer, which for which it is given that she sings with a sound intensity of 1.9 times 10 to the minus 5 watt per meter squared. Just by looking at the units, you can tell that this is the intensity of the wave. Okay, this is the intensity of the sound waves that her voice is producing. What is her sound intensity level that an audience member hears? It's pretty straightforward. We're looking for what beta is, given that we have I as 1.9 times 10 to the minus 5 watt per meter squared. So beta, as we have seen, is defined as 10 decibels times logarithm of I over I naught. And I naught is the lower limit intensity of the human hearing, which is 10 to the minus 12 watt per meter squared, and that's always a constant, okay, for all our purposes. And therefore, beta becomes 10 times log of I. What is I? In our case, I is 1.9 times 10 to the minus 5 watt per meter squared, divided by I naught, which is 10 to the minus 12 watt per meter squared. So the watt per meter squareds go away, and we only have units of decibels, which was attached to this 10. If you calculate this out, first divide these two, that's always easier, and then take the logarithm of that, multiply that by 10, your calculator should spit out a value of 72.8 decibels. So this is the intensity level of the sound that the audience member hears, while the intensity of the sound was this much. Okay, so I hope this clarifies the difference between an intensity and intensity level. Very shortly, if you cannot understand the quite grasp the differences, just look at their units. If something is given in watt per meter squared, we're talking about intensity. Something is given in decibels, we're talking about intensity levels. Okay, if you're asked to find intensity level, think about beta. If you are asked to find intensity, think about watt per meter squared and this formula right here. Okay, I hope this lecture made sense. Thank you very much.